All right, next let's go over question 2. So question 2 says a business college decides to accept only the top 10% of the applicants applying. Their acceptance is based on performance of an entrance exam. The mean score is 75 and the standard deviation is 10. Now, make sure whenever you're doing questions like this, somewhere you put the fact that it's normally distributed with the mean of 75 and standard deviation of 10. So you want to put, you can even just do it at the top, approximately normally distributed of 75, 10, and that automatically applies throughout the entire question here. Now, let's look and see what this says. This says, what is the minimum score needed to be accepted to the university? So it says that the top 10% are accepted at the university. So if we draw a line on my normal curve, the top 10% here are the only people that are getting accepted, and the 90% below it are not, okay? So we want to find what this minimum score is. So remember, the first thing we have to do is figure out what that z-score is. So on your graphing calculator, you're going to use inverse norm. Remember, inverse norm is like the opposite of the normal CDF. Instead of you taking the z-score and getting the probability, we're now giving the calculator the probability and giving us the z-score. Okay, so keep in mind here, you're going to do inverse norm of 0.90, because remember when you do this, it always gives you the area to the left. So what is the area to the left of it? That's your 90%. So this z-score right here is going to be 1.286. Now we're going to use our z-score formula, which remember is z is your sample minus the mean divided by your standard deviation. We know the z-score. We don't know the sample score. We know the mean. We know the standard deviation. So we're going to solve that and just say the minimum score needed to be accepted is an 88. Or you could leave it as 87.816. Now, you can also do this on your graphing calculator. I understand by doing inverse norm and then putting 0.90, and then you can put the mean 75 and standard deviation of 10. That will automatically give you that 87.816. That's fine. You can do that. You still have to show this work for your z-score. All right, so letter B says, what is the probability that a randomly selected student will score higher than a 92? All right, so make sure that you're showing all these steps. Number 1, what is the probability that they're scoring higher than a 92? Then you must show this work for your z-score. 92 minus your mean divided by your standard deviation gives you a z-score of 1.7. What's the probability that it's larger than 1.7? That's 0.0045. So the steps that you would have to show are 1, this probability statement with X. 2, the work for your z-score. 3, your probability statement with Z. 4, you're going to need to show your graph, and 5, you need to show your answer, okay? So your graph is saying the probability, 92, of anything higher than that. So that's your graph with your area shaded in. All right, now letter C says, what is the percentile rank of a student who scored 70 on the exam? Now remember, percentile rank is at that score or below. Okay, so here the percentile, if they scored a 70, what percent is below it? So now here's my probability statement. X is less than 70. Here's the work for my z-score. Here's my z-score. Now remember, to get this here, to get that probability statement, you're going to use the normal CDF. So you're going to do normal CDF. Okay, lower bound is negative 1,000 since it's got anything below 70. Upper bound is that 0.3085. And that will give you, I lied. I wrote that wrong. That's your answer. Okay, the upper bound is the negative 0.5. Okay, and that's going to give you the area from negative 1,000 to negative 0.5 because that's my z-score. Okay, which is going to be your 0.3085. Okay, now you can also type that into your calculator and get the answer if you did normal CDF and you did your lower bound was negative 1,000, your upper bound was 70, typed in the mean of 75, standard deviation of 10, it would automatically give you that 0.3085, but you have to show this work. You will not get full credit on your midterm if you do not show 1, your probability statement, 2, your z-score, 3, probability with z-score, 4, your graph, and 5, your probability statement. All right, let's take a look at interpreting the standard deviation. So a business from our same question here, I'm not going to read it again. The standard deviation of the scores was 10. Remember, our standard deviation is the distance from the mean, but you want to put it in context. You cannot just state the distance from the mean was blank. So it's the distance between the score of each applicant. The distance between the score of each applicant and the mean score was on average 10 points. So your standard deviation is the average distance from the mean. And in this case, we're talking about the score of an applicant. So the distance between the score of an applicant and the mean score was on average 10 points. All right, now let's take a look at this next question. This is going to be going over reviewing experimental data and observational data. Okay, the National Hawthorne Study, I believe I spelled that wrong. No, I didn't. The National Halothane Study was a major investigation of the safety of anesthetics. Records of over 850,000 operations performed in 34 major hospitals showed the following death rates for 4 common anesthetics. So here's our death rate for anesthetic 1, 2, 3, and 4. There seems to be a clear association between the anesthetic used and the death rate. So if we take a look right here, C looks like, oh, that's a much higher death rate, and A and B are much lower death rates because they're only 1.7 versus 3.4. All right, let's take a look at these 2 questions. So explain why we call the National Halothane Study an observational study rather than experiment, even though it compared the results of using different anesthetics in actual surgery. So in order for this to be an experiment, we would have to have the treatments randomly assigned to the subjects. Well, that was not the case here. These treatments were already given and we were just looking at the results. So the different anesthetics were not randomly assigned to the subjects. Okay, and remember there are 2 important aspects of experimental design. What does random assignment do? Random assignment allows you to establish cause and effect between the treatment and the outcome, and random selection allows us to use the results towards the larger population. If there's no random selection, you can only apply it to those in your group, okay? When the study looked at other variables that are related to a doctor's choice for anesthetics, it found that anesthetic C was not actually causing any extra deaths. Explain the concept of confounding in this context. Now notice how it says, we're doing 2 things. We're explaining confounding in context. So you cannot just say what confounding does. It has to be in the study. And identify a variable that might be confounded with the doctor's choice of anesthetic. Now, here's just my example. This is not the only one that's true. So remember, confounding what means is in the end, we aren't going to be sure if it's the anesthetic that caused the death or something else. So 1 could be this type of surgery. If anesthetic C is used more often with a type of surgery that's a higher death rate, then we wouldn't know if the death rate was higher because of the anesthesia or the type of surgery. Remember, confounding messes with your explanatory variable or your anesthesia. In the end, we don't know what it is. Maybe anesthesia C is only used in very elderly patients, and therefore we're not sure if they died because they were not in good of health conditions when they underwent surgery, or if it was actually that anesthetic. All right, in a recent month, 88% of automobile drivers filled their vehicles with regular gasoline. 2% purchased mid-range gas, 10% bought premium gas. Of those who bought regular gas, 28% paid with a credit card. Of those who bought mid-grade gas, 34% with a credit card, and 42. So the 34 goes with the mid-grade and the 42 is with the premium. respectively, paid with a credit card. Suppose we select a customer at random. We're going to draw a tree diagram to represent the situation. And we know we have a tree diagram because we have multiple probabilities going on. All right, so number one, we're talking about 3 types of gasoline: regular, mid-grade, and premium. So we know that 88% purchased with regular. We know that 2% purchased mid-grade and 10% bought premium. Okay, so this is our regular, mid-grade, premium. Now remember, this in all of your branches always have to add up to 100%. Okay, now of those, we're going to talk about those who paid with credit cards and those that did not. Of those that bought regular, 28% paid with credit card. Now, these branches have to add up to 100, so we're going to take 1 minus 0.28 to figure out the amount that did not pay with credit card, and that is going to be 0.72. Okay. For customers who bought mid-grade gas, 34% paid with credit card. So we're going to subtract 1 in order to get 100%, so that's going to give us 0.66 that did not pay with credit card. And those that bought premium gas, 42% paid with credit card. So therefore, that is going to be 58% that did not pay with credit card. Now, this branch adds up to 1, this branch adds up to 1, and this branch adds up to 1. Now, when you're doing this, you always want to multiply across the branches because this is going to be regular and paid with credit card, regular, not credit card, mid-grade, and credit card, mid-grade, not credit card, premium and credit card, premium, not credit card. So let's just take a look and see what that looks like. So notice I multiplied across the branches. So here is regular and credit card. And notice how there's 3 different ways they can pay with credit card. If they buy regular, mid-range, or premium. All right, now let's take a look at the 2 questions. Find the probability that the customer paid with a credit card. So we basically want the probability that they paid with a credit card. So look at the end of your branches. So there are 3 different ways they paid with a credit card. 1 with regular gas, 2 with mid-range, and 3 with premium. So we need to add up these 3 probabilities. Okay, that's why it's important to make sure you multiply across the end of your branches. Now, the next question says, given the customer paid with a credit card, find the probability that she bought premium gas. So this is where you're going to use your conditional statement. What are we finding? We're finding the probability that they got premium gas, given what do we know first? That they paid with a credit card. Okay, now this, remember your formula. Okay, premium given, that's what we already know. We already know that they've paid with a credit card. So premium gas, given that they've paid with credit card, is the probability of both occurring, premium gas and credit card, all over the probability of just paying with a credit card. You need to show this fraction, the 2 decimals divided by each other. That is really important to make sure you do. Now, go back to our tree diagram and say premium gas and credit card. That's this portion right here. That's the 0.042. What's the probability they paid with a credit card? You had to add those 3 branches to get that answer. Divide the 2 and you get the answer. Now, the next question says, how can you prove if getting premium gas and using a credit card are independent? So that's what you would want to check. Okay, remember it's the probability of A given B would have to be the same as the probability of A because B is not affecting A. So how can we prove if getting premium gas and using a credit card are independent? Okay, so we can use our statement here. So the probability of premium given that they use a credit card has to be the same as the probability of premium. Well, if we look here, the probability of premium given that it's a credit card, that was from this statement right here. That was 0.142. The probability of premium gas, notice, was just 0.1. So therefore, since those are not the same, they're not independent.